Yeah. Okay. Today I'm going to introduce the influences of the serrated trailing edge on flapping wing aeroacoustics and aerodynamics. My name is Xueyu, and I'm a PhD student in UNSW Canberra. And my PhD study focus on the computational fluid dynamics and computational aeroacoustics. And let's talk about the outline today. The first part is the introduction about the flapping wing and the serrated trailing edge. And I'm going to show you the methodologies I used and the physical model, also the validations and results. Finally, the conclusions. And let's go to the first part. When you think about the aircraft, the first thing you think about maybe the fixed wing aircraft. A typical example of the fixed wing aircraft is just like this, a Su-34. You can see that you have two wings in the lateral, while the aircraft is driven by the jet. And you can find a lot of examples, and nowadays it is commonly used by the commercial airplane. However, in nature, the animals, just like birds or some insects, they can fly not by the jet. Instead, they use the flapping wing. Just what I'm showing you in the figure 1. Here is a hovering human bird. You can see that with the flapping motion, the human bird can generate enough lift to maintain their flight. And if you look at the picture, you can find that the vertical structure in this case is represented by the red color. You can find that when the wing is flapping, it can generate the leading edge vortex and the tip vortex. And those vortexes can create the low pressure region, which can create a pressure difference to maintain their flight. And compare with the traditional fixed wing aircraft, the flapping wing can generate enough lift force with smaller size, and it has a higher maneuverability. And by these characteristics, the flapping wing micro-aerial vehicle was developed. And this is a typical example. And it has high lift and small size with high maneuverability. And it can be used for many purposes. For example, the military purpose, the reconnaissance, and for the civic purpose, the environment monitor. Apart from that, it can also be used for the energy harvester. Here is a diagram for the flapping wing energy harvester. You can find that in the left-hand side, there is incoming flow, and we actively make the wing pitching so that we can use those vortex to generate a force in vertical direction, so that we can drive the flywheel to generate the electricity, for example. And there are many applications for the flapping wing. And there are so many studies towards the aerodynamics of the flapping wing before. However, there are just a few studies covering the aeroacoustics of the flapping wing. And actually, according to a study, the flapping frequency ranges from 12 to 120 hertz. And this is mostly within the audible range of human hearing. So it is very important to study the noise associated with the flapping motion and see if we can figure out a solution to reduce the noise. And yeah, in this section, I'm going to introduce the acoustic study towards the flapping wing. So previously, people used the experimental study to record the noise generated by a flying fly. And you can see this is an experimental setup. And you need to put the microphone here. And you need to put an insect here to let it fly, and you record the noise. It is very complicated, and it's also very expensive for this whole experimental setup. And the other option is the numerical studies. And as for numerical studies, we have two types of numerical solution. The first time is the direct numerical simulations. It is based on the compressible Navier-Stokes equations. Because the sound is a byproduct of the compressibility. And it is very accurate because typically we use the high resolution scheme with low dispersion and dissipation. But the computational cost is very large, especially for the 3D case, because we need to set the buff zone to prevent the reflection of the sound, so that we can get the accurate sound pressure fluctuation. And for the hybrid method, you can either use compressible NS equation or incompressible NS equations. The flow field and sound field are separated, which means that they are independent. The sound field will not affect the flow field. And the sound field is usually solved by the acoustic analogy or some other method like linear Euler equations. The solutions from the flow field acting as the input for the sound field, which means that we firstly solve the compressible or incompressible NS equations, and the solution will be the input for solving the acoustic analogy. This is called the hybrid method, and it's the method we are going to use here because it has much less computational cost. And let's talk about the serrated trailing edge. And you can see, if you look at the first picture, this is a ring profile of the great O, because the O can fly silently, and people think about what results in the silent flight. And when they observe the ring profile, they found that the trailing edge is not straight; it is serrated. And people think about if this trailing edge serrations result in the noise reduction. And in last few decades, there are so many studies focused on the influence of the serrated trailing edge on the aeroacoustics of the fixed wing. And they prove that the serrated trailing edge can effectively suppress the noise. However, such configuration has never been used for the flapping wing. And this is a research gap. And in this study, we are going to apply the serrated trailing edge to the flapping wing to see if this configuration can improve the aerodynamic performance and decrease the noise. And let's talk about the methodologies. The flow solver we use is the three-dimensional dimensionless incompressible NS equation. It is implemented in curvilinear coordinate. And you can see the control equations here. The second or the central difference scheme is for the convection, the viscous and pressure term here. And second order Crank-Nicholson scheme for the tide advancement. And this is for the full solver. And because the flapping wing is different from the stationary wing, you need, the position of the wing will change from time to time. And if you use the traditional method like the ALE, we need to regenerate the mesh step by step when the wing is flapping. And therefore, the immersed boundary method was proposed by Pushkin in last century. And generally, the immersed boundary method can be divided into two categories. The first one is the sharp interface. It is accurate, but complicated for implementation. And it could generate the unwanted numerical oscillations when the interface is changing step by step. And the other method is the diffuse interface immersed boundary method, which we call DIB. It is very easy to implement, and it can reduce the numerical oscillations because the numerical oscillations can affect the acoustic simulation. So we want to mitigate such the oscillations. And let's talk about the methodologies for the DIB. And let me show you the second picture first. You can see that actually the wing surface is discretized by the triangle surface mesh. And the surface mesh is actually the Lagrangian marker because it is moving along with the wing step by step. And if we look at the first picture, you can find that the red square represented the Lagrangian marker, which is the triangle mesh in this diagram. And then to implement the DIB, the first step, we need to use the interpolation because we have the black circle here. This is the fluid shell, the Cartesian fluid shell. And we need to use the interpolation scheme, the delta function, and you can find the details here, to interpolate the velocity at the red square. And then we can calculate the Lagrangian force. And then we can spare the Lagrangian force to the adjacent cells. And this term is included in the NS equation. With this strategy, we can the no-slip boundary condition can be achieved at the wing surface, and we don't need to regenerate the mesh. And this is the outline of the DIB. And let's talk about the surface pressure. Oh, sorry. Let's talk about the surface pressure. This picture I showed you before. And because we need to do the acoustic simulation, we need to know the surface pressure at the triangle center for the mesh. And because the triangle mesh is not coincide with the Cartesian mesh, we need to interpolate the surface mesh. And here I show you the scheme for surface pressure interpolation. And still we get the Lagrangian marker, which is the triangle mesh center. We call it as point A. And then via the normal vector, we extended the point A to point B so that we can get the point B here. And the length between point A and B is denoted as delta L. And then the gradients from point B to point A must satisfy this equation so that we can calculate the pressure at point A via this equation. And this is the scheme for surface pressure interpolation. And let's talk about the acoustic solver. In this case, we use the Farassat formulation 1A to do the acoustic simulation. Actually, this formulation is a solution of the Williams-Hawking acoustic energy. And because the Mach number in this for the flapping wing is very low, it's far less than 1, so that we can ignore the quadrupole source. We can only consider the monopole and dipole source. And with the green function, we can get the expression of the monopole source, and the dipole source is the integral solution. You just need to know the surface pressure and surface velocity. You can calculate the sound pressure for a given observer. And the total sound pressure for a given observation location S is equal to the summation of the thickness noise and loading noise. But if you look at the equation, you can find that here we got the RET. It means the retardation time, because if you look at this picture, you can find that here we got the origin, and we have a source location, the wing surface, the source location Y, and we have a observer location S, and the R is from the source location to the observer location, and the expression is this equation. Because we have a sound signal generated at Y at the time step tau will span R over CO before it arrives the observer location, and the CO is the sound is the speed of sound, because the sound signal will travel with the speed of sound along the R, and this is how the definition of the retardation time. And let's talk about the details of the implementation of the retardation time. Firstly, we have a source time, tau n, and then with the R we can calculate the observer time, TP. But TP is not exactly coincide with the recorded time step, and we need to decompose the signal at this time step into two neighboring signals, and we can do it via these two equations. And then we repeat the former the step A to step C for all the source time steps, and this is how we implement the Farassat formulation 1A. And let's talk about the physical model. And you can see in this picture we have a low aspect ratio wing with the aspect ratio equal to 2, and the wing undergoes the stroke, which is the rotation around the z-axis, and the pitching motion. The pitching is the rotation around the leading edge, and this is the equation for these two motions. And at the bottom you can see the schematic of the stroke and pitching motion. Here is the upstroke and here's the downstroke. And the Reynolds number we chosen is 310. It is a reasonable Reynolds number for insect flight. And the Mach number is chosen as 0.012. It's also a reasonable Mach number for the insect flight. And the reference velocity is the mean tip velocity. And the flapping frequency in this case is 0.2, which means that the F here is 0.2. And here I show you the computational domain and boundary conditions. Actually in this case, because it is hovering, we use a cubic computational domain, and the length of the cube is 15c. And if you look at the second picture, here I show you the mesh profile. You can see that we create a small room here to enclose the wing to ensure that the near wall vertical structure can be accurately resolved. And for the outer region, we use the stretch mesh. And for the boundary conditions, the outer boundary, we use the free slip boundary condition. At the wing surface, we use the no slip boundary condition achieved by the DIB. And the validations, we present the CL because we don't have the data at RE equal to 310. So we conduct another simulation at RE equal to 176 and compare with the previous studies, and we found that the CL from our solver agrees well with the previous data. And for the Reynolds number 310, we conduct the grid converged test for the inner region, and we found that the grid arrangement is okay, and we are going to use the medium mesh for the following study. And also for the acoustic solver validation, we calculate the SP, the sound pressure level at R equal to 14C from the period point in the XY plane. And this is the definition of the sound pressure level. And we compare with the previous data solved by the direct numerical simulation. And we found that the discrepancy between our data marked by the red line with the DNS is less than 2 decibel, with the maximum discrepancy less than 2 decibel, which is good. Yeah, we finished the validation, and now I'm going to introduce the trailing edge serrations. Let's look at the first picture. You can find that this case is what we call the baseline case, and then we apply the serrated trailing edge. Here, you can see in this case we only use the square wave serrated trailing edge because it is simple and easy to resolve. And we consider 2 parameters. The first one is the wave number, non-dimensionalized wave number, and also the wave amplitude with the definition in the bracket. And here in the table, we have 20 different trailing edge serrations with different wave amplitude and different wave number. And yeah, well, in this slide, I'm going to introduce the trailing edge serrations, how the trailing edge serrations affect the average lift coefficient. This is the contour of the average lift coefficients for different cases. As you can see, here is the baseline. When the 2h star equal to 0 is the baseline, and if the wave number is low, then with the increment of the wave amplitude, the average lift coefficient is decreased. But when the wave number is high, when you increase the wave amplitude, then the average lift coefficient is increased. And for a given wave amplitude, the average lift coefficient is increased with the increase of wave number. And to better study how the serrations affects the lift coefficient, I have chosen 3 cases to start their instantaneous lift coefficient. The first case is the baseline, and the second case is D1 with the minimum average lift coefficient. And the third case is D5 with the maximum lift coefficient. And you can see here, I show you the instantaneous lift coefficient in half cycle. And I also pick up 3 time step, and the first time step is 0.25, the second is 0.3, and the third is 0.375. And it can be found that for the first time step, the D5 in the baseline is close and larger than D1, while for the second time step, the D5 is the maximum, while the baseline is the second, and D1 is also the minimum. Well, for the first time step, you can find that D1 and the baseline are very close, and D5 is much larger than the other 2s. And in the next slide, what I'm going to show you is the instantaneous vertical structure and the surface pressure coefficient at this 3 time step. If we look at the t equal to 0.25, you can find that the low negative CP in the mid-span accounts for the low CL for the D1 case. And for these 2 cases, the surface pressure distribution is similar. I mean, for a given span-wise position. But if you look at the tip vortex, you can find that the baseline has a larger tip vortex than the d phi. And for the second time step, you can find that D1 has also has the lower negative CP here. And if you look at the d phi, especially at this region, you can find that the negative CP is higher than that of the baseline, which accounts for the highest CL. And for this time step, you can find that near the trailing edge, the CP is still the lowest, is still the highest, and that's why the lift coefficient of d phi is higher than the other two cases. And let's talk about the influences of the serrated trailing edge on the aeroacoustics. And firstly, we need to calculate the sound power level for all the cases. And in this slide, I defined the stroke Haar number. I defined the stroke Haar number here. And remember, ST equal to 0.2 is the flapping frequency. And we need to calculate the sound power levels. Therefore, we define a surface S here. And the radius is equal to 100 C, while the center of this sphere is the period point. And let's look at this equation first. We calculate, in this bracket, this is the definition of the sound power level, and F is the FFT, which means that in this step, we use the FFT to convert the signal into the frequency domain. And then we can calculate the Wu mean square for a given frequency. And then we can convert the sound power level into frequency domain. And then we divided the frequency range into two frequency band. The first is ST from 0 to 2. The second is from 2 to 4. And the maximum frequency we studied is 4 because the corresponding wavelength is around 21 column, which is much larger than one column, because we use the free green function and the incompressible NS equations, which means that we cannot consider the solid sound interaction. Therefore, we need to ensure that the wing is a compact source. That's why the maximum frequency we study is 4. And we also calculate the average sound power level at STA, and also the average sound power level at STB for all the cases. And here I show you the sound power level for all the cases. You can find that at the first frequency band, here's the baseline. With the serrated trailing edge, you can find that it firstly increased with the wave amplitude and then decreased. For a given wave number, the minimum value is achieved at the maximum wave amplitude we study. However, if you look at the scale for the sound power level here, you can find that although it looks you have reduction or you have some increases. However, we can say that because it's almost less than 1 decibel, we can say that the serrated trailing edge has little influences on the sound power level for the average sound power level for the first frequency band. And then for the second frequency band, we can find that the reduction is very significant. The maximum reduction you can find is around 8 decibel. It's achieved by K star equal to 6 pi and 2H star equal to 1.5. Yeah, it's non-trivial, but if you look at this case, when the K star equal to 8 pi, the reduction is also around 7 decibel, and it's also very large. And more importantly, D4 can maintain the lift coefficient, while for this case, the lift coefficient is reduced. And it's very interesting because we found that D4 can maintain the lift coefficient, and it can also reduce the noise at the second frequency band. Therefore, this case is picked up and compared with the baseline for the following studies. And in this case, we studied the serrated trailing edge, the influences of serrated trailing edge on the directivity. And you can find that we have, I have calculated some power level at given frequency for D4 and the baseline. You can find that when at ST equal to 0.2, which is the flapping frequency, and ST equal to 0.4, which is 2 times of flapping frequency, the directivity of the D4 and the baseline is very close. And when the ST equal to 2.2 and ST equal to 2.4, you can find that the solid line is the D4. D4 is much smaller than the baseline, which means that the second frequency, you can find that the serration has changed the directivity for the higher frequency, and this is the findings. And you can see the instantaneous sound pressure in SY plane, but I'm not going to adjust this picture because it's just a demonstration. And to find out the reason for the noise reduction, we studied the surface pressure fluctuation. And in this picture, I calculate the average surface pressure fluctuation in these two frequency bands. For the first frequency band, the average surface fluctuation, you can find that D4 has decreased the surface pressure fluctuation compared with the baseline. And for the second case, the reduction is more obvious, especially near the wingtip. You can find that compared with the wingtip of the baseline, the wingtip of the D4 has much smaller pressure fluctuation. And this should be the reason for the noise reduction. And to further confirm this assumption, I conduct another test for the noise reduction, for studying the noise reduction mechanism. And you can see that I divided the wing into 3 parts. The first part corresponding to the region near the wing root, and here is the midband. And for the third part, this part is the wingtip. Yeah, and you can find the diagram here. And because the total sound pressure fluctuation is equal to the sound pressure fluctuation caused by the first part, past the second part, past the third part. And here I pick up 2 points and study the power spectrum density of the sound pressure at these 2 points. And this 2 point has a radius of 14 C from the pivot point. And let's look at the total sound pressure at P1. You can find that at ST larger than 1.5, the PSD of D4 is much slower. It's much smaller than that of the baseline. The same finding can also be found for P2. And then in next slide, I studied the PSD created by the first part at P1 and P2, and also second part and third part. If you look at the first row, you can find that D4 has actually increased the PSD for both points, which means that the part one, the part near the ring root has increased the total noise. And let's look at the second part. You can find that for both points, D4 has not decreased the noise significantly for both points, which means that the second part is also not the reason for the noise reduction. And when it comes to the third part, you can find that the similar distribution in frequency with the total noise can be found for the part 3. If you look at the picture and compare with the third row, you can find that it is quite similar, which means that the part 3 has been confirmed as the reason for the noise reduction. And because the lift coefficient is not decreased by the serration, and while we can achieve the noise reduction, and here we conducted a study towards the lift coefficient. We separate the lift coefficient into 2 parts. The first part is caused by the pressure, and the second part is caused by the shear stress. And here, I show you the instantaneous lift coefficient in a flapping cycle. The first picture is caused by the pressure, the lift coefficient caused by the pressure for the D4 and the baseline. It can be found that the baseline has higher lift caused by the pressure than that of the baseline. However, when you comes to the shear stress, you can find that D4 has higher lift caused by the shear stress than the baseline, which means that although the D4 has a less pressure, has less pressure caused lift, but it has a higher shear stress caused lift. And also we conducted the lift, such analysis for all the simulation groups. We found that the average lift caused by pressure and the average lift caused by the shear stress here. You can find that with the increase of the wave amplitude, this parameter is decreased. And on the contrary, with the increase of the wave amplitude, the one with higher wave number has higher lift induced shear induced lift. Yeah, and this can be explained why we have a similar, why D4 has a similar lift with lower noise. And the conclusion is that the serration can decrease the average sound power level in STB, and the change in wingtip vortex result in the low pressure fluctuation at wingtip. The reduction of the pressure contribute lift was compensated by the shear stress contributed lift. And this is the conclusion. So any question? This is the end of my talk.